Welcome back to The Explainer. Okay, I am absolutely thrilled to get into this one today because we're looking at the thermal frontier of space-based AI computation. Now, I know what you're thinking. Sending these massive data centers that train our AI models up into orbit, it sounds like the ultimate sci-fi dream, right? I mean, you've got limitless solar energy up there and endless physical room to expand. But as it turns out, there is this massive, highly counterintuitive physics problem standing squarely in our way. Let's dive right in. So here's the big question. If space is freezing cold, which, we all intuitively understand that it is, why on earth is cooling a computer the absolute hardest part of putting AI in orbit? We really need to shatter this misconception right off the bat. It's so natural to think of space as this giant freezing refrigerator. You just open the door and boom, the heat escapes. But actually, that is not at all how physics operates in a vacuum. Think about it. Down here on Earth, we have so many incredibly easy, accessible ways to cool massive data centers. We use air cooling with giant fans. We pump water or dielectric fluids. We use evaporative cooling. We can literally just dump our waste heat right into the atmosphere around us. But in the vacuum of space, there is essentially no atmosphere. You can't just open a window to let it breeze in. Convection just flat out doesn't exist. The absolute only way to reject waste heat is strictly through thermal radiation. And that brings us to the ruthless dictator of space engineering, the Stefan Boltzmann law. Now, without getting bogged down in the textbook math, this law boils down to one very cruel reality. Because thermal radiation is literally your only tool for cooling, the amount of heat you can dump is entirely bottlenecked by your surface area. That's it. If you want to dump a massive amount of heat, you have absolutely no choice but to build a massively large surface.
Let's just let that sink in with a real-world example, just to see how crazy this gets. Say we want to launch a 1 gigawatt AI supercluster into orbit. Almost every single watt of electrical power that goes into those computers eventually turns into a watt of waste heat. So we've got 1 gigawatt of heat to reject. If we want our space radiators to run at a pretty standard 27 degrees Celsius, the surface area we need is an enormous 2 to 4 million square meters.
Let's just pause for a second. 2 to 4 million square meters. That translates to 2 to 4 square kilometers of continuous radiator surface. That is literally larger than many urban downtown districts. Imagine flying a sheet of metal the size of downtown Manhattan through low Earth orbit just to keep your computers from melting. It's a completely staggering spatial requirement. So if a standard data center is that bad, why does AI specifically make this entire situation so much worse? Well, modern AI hardware is just insanely power dense. Today, a single rack of advanced AI accelerators can pull anywhere from 50 to 150 kilowatts. And we know for a fact that future AI training clusters are going to easily hit hundreds of megawatts or even multiple gigawatts. Because these chips draw so much juice, the engineering math does something really weird. The dominant mass of your multi-billion-dollar orbital facility won't even be the compute hardware. The gigantic radiator system you need to keep it cool will actually weigh significantly more than the GPUs themselves. Crazy, right? And just getting that heat out is an agonizing 4-step gauntlet. First, you have to collect the heat directly off those scorching hot chips. Then, you've got to pump it efficiently through this intricate maze of coolant pipes. Third, transport it across those kilometer-scale structures we just talked about. And finally, radiate it out into the void of deep space. Every single phase of this plumbing nightmare introduces massive weight, incredible complexity, and just so many potential points of failure. But hey, engineers aren't just giving up. They're dreaming up some truly wild sci-fi level solutions to tackle this gigawatt heat problem. Let's rapid fire through 5 of the most fascinating ones right now. Solution number 1 is the brute force approach. Giant deployable radiators. Think of huge, lightweight panels with heat pipes, very similar to what keeps the International Space Station cool right now, just scaled up drastically. The pros? It's proven physics. No exotic, untested tech needed. But the con is massive. You are building a giant, fragile kite in orbit. It makes your multi-billion-dollar AI center a massive target for fast-moving micrometeoroids. Okay, solution 2 takes a completely different angle: high-temperature computing. Remember our old friend, the Stefan Boltzmann law? Because radiated power scales exponentially. If we can engineer our electronics to run much hotter, say doubling the operating temp to 600 Kelvin, we increase the radiation by 16 times. That shrinks your city-sized radiator down drastically. The catch, of course, is that you need specialized semiconductor materials and boiling hot coolant loops that won't literally melt your multi-million-dollar hardware. If flying a giant radiator in free-floating orbit is too risky, what about solution 3, lunar-based data centers? Instead of a space station, we just build the AI facility right on the moon. This is brilliant because it's easier to construct, you can use local materials, and maybe even set up nuclear power. The coolest part? You use the lunar regolith, the actual moon dust, as a massive thermal sponge, and hide your radiators deep inside permanently shadowed craters. You're still radiating heat, but having a solid surface means your cooling infrastructure can be way heavier and much more robust. Now, solution 4 is where things go full sci-fi, rotating droplet radiators. This is an actual advanced concept studied by NASA. Instead of heavy metal panels, you literally spray continuous streams of liquid coolant straight into the vacuum of space. The droplets radiate their heat away as they fly through the void, and then a collector physically catches the cooled droplets to pump them back over the chips. It saves an unbelievable amount of weight and creates huge surface area. But as you can probably guess, the control systems are a nightmare, and the risk of losing your coolant into space is a colossal challenge. And finally, we have solution 5, beamed power and distributed compute. Instead of building one giant heat-choked supercenter, why not just break it up? You launch a swarm of smaller orbital compute nodes, spreading the heat generation across a massive orbital constellation. Then you use lasers or microwave beams to transfer power and data between all the separate facilities. It's a super elegant way to avoid concentrating gigawatts of waste heat into one single, impossible-to-manage location. But look, at the end of the day, all of these engineering marvels crash headfirst into the exact same underlying reality, the fundamental limit of space infrastructure. It all comes down to this golden rule of aerospace engineering. Power generation in space is relatively easy, but waste heat rejection is incredibly hard. Throwing up a massive solar array to generate gigawatts of electricity in unobstructed sunlight, we know how to do that. But every single watt those AI chips consume must be radiated away. For engineers, heat rejection, not launch costs, not solar panels, not the chips themselves, is the absolute primary bottleneck for truly massive orbital AI. Which leaves us with this final, genuinely provocative question. If the thermal cooling system actually outweighs the GPUs, the memory, and the power systems combined, what are our future orbital megastructures actually going to look like? When we look up at the night sky a few decades from now, the giant AI data centers floating above us aren't going to look like supercomputers at all. They're basically going to be endless, sprawling oceans of radiators. It completely flips our entire vision of off-world technology on its head. Thank you so much for joining me on this explainer. I really hope it shifted your perspective on the final frontier of computing just as much as it did mine. See you next time.